So let's recap what we talked about, right? So last week on Thursday, we introduced this idea of Vieta's formulas, which allow us to get some relationships regarding the roots of polynomials without having to find the roots themselves. We can get these relationships just by looking at the coefficients of our polynomial. So the first case we looked at was the degree 2 case, right, where a polynomial was something of the form a2x squared plus a1x plus a naught, right? And we normally wrote that as ax squared plus bx plus c, but this is a little more general. And we said that the sum of the roots was the negative of the coefficient on the second highest degree term. So it's the negative of the coefficient on x in this case, divided by the coefficient on x squared, right? And with using ax squared plus bx plus c, we said that that was negative b over a. And the product of the roots was the constant term divided by the coefficient on x squared. So the product of the roots was c over a. This sounds familiar? Cool. We also extended this to the degree 3 case when we looked at polynomials of the form a3x cubed plus a2x squared plus a1x plus a naught. The sum of the roots was then negative a2 divided by a3. And notice we're always going to have this divided by coefficient of the highest power term, right? So the sum of the roots was negative a2 over a3. The product of the roots was negative a naught over a3. And notice in the degree 2 case, the product of the roots was not negative. Or well, it may be negative, but there's no minus sign out front. Right here, there's no minus sign. Whereas down here, there is a minus sign. And the reason for that is because we're multiplying 3 of the roots together, but the roots are written as, x minus r1, x minus r2, x minus r3. So there's an odd number of them. You multiply them, you get a negative sign. But also, we were left with this weird term, which is the coefficient on x, right? And we called this a symmetric sum. Well, they're really all symmetric sums, but this one was the sum of all possible ways I could take 2 of my 3 roots and multiply them together. Right? I have my 3 roots, r1, r2, and r3. All possible ways I can choose 2 of them. Well, I can take the first and second, first and third, or second and third, right? Because 3 choose 2 gives me 3 ways. And it's the sum of all possible ways I can multiply those 2 things. So I multiply first and second, multiply first and third, multiply second and third. Is that okay? Cool. And if we really want to be general, this is also a similar thing. It's all possible ways we can choose one of our roots, multiply them together, and add them. Well, to choose one root, we just pick r1 on its own, or r2 on its own, or r3 on its own. You multiply r1 by nothing, it's still just r1, right? And you sum those together. And lastly, it's the sum of all the ways we can multiply 3 of our roots together, right? And well, there's only one way you can do that because 3 choose 3 is just 1. I take all of them, r1 times r2 times r3. So there's 3 choose 3, which is 1 term in the sum. Here, there's 3 choose 2, which is 3 terms in the sum. Here, there's 3 choose 1, which is 3 terms. Is all of this okay? Cool. And then we generalized it for polynomials of degree n, right? And so we have this weird general formula, which on its own is not particularly meaningful, but it's more about being able to generalize the pattern for arbitrary polynomials. Okay? All you have to know is that terms that are the sums that look like this are just sums of products of the roots taken in different quantities. Okay, and that perhaps becomes a little more clear when we look at the degree 4 case. So suppose we look at x minus r1, x minus r2, x minus r3, and x minus r4. Well, what will our coefficients look like? Well, we'll have 1 x to the 4 minus, now the sum of the roots on their own, plus, because it's going to alternate, the sum of the roots multiplied in pairs. So now we'll have r1 times r2, r1 times r3, R1 times R4, so on and so forth, right? R1, R2 plus R1, R3 plus R1, 4, R2, R3, R2, R4, R3, R4, x squared, minus, now it's going to be the product, or the sum of the product of all the ways I can choose 3 of the roots and multiply them. So what will I have then? R1, R2, R3, R1, R2, R4. And the way I'm thinking about this is, well, if I'm multiplying 3 of them together, it's just choosing one of them to not multiply, and then multiplying the rest. Right? So here, I'm excluding R4. Here, I'm excluding R3. Then I'll exclude R2. And then lastly, I'll exclude R1. That's how I know I've done all of them. And then lastly, it's the product of all the roots together. So then plus R1, R2, R3, R4. Is that clear? So I'm just multiplying the roots, taken in pairs, or taking 3 at a time, or taking 4 at a time. And that explains why here there's 4 choose 2 terms in this sum. And here there's 4 choose 3. And for example, in here, 4 choose 1 terms, and so on and so forth. There's 4 choose 2 because there's 4 choose 2, or 6 ways I can pick 2 of the roots, just multiplying them and adding. Okay? And a probably more useful general pattern is the one for the sum of the roots and the product of the roots. So the sum of the roots is always the negative of the coefficient on the second highest degree term divided by the coefficient on the highest degree term. Okay? And so that's one you definitely will want to remember. And then the product of the roots is always the constant term, so the coefficient at the very end, divided by the coefficient on the largest degree term. But sometimes it's positive and sometimes it's negative. So that's why we have negative 1 to the exponent n. Right? So back in the degree 2 case, we noticed that this term didn't have a negative 1 out front. In the degree 3 case, it did have a negative 1 out front. In the degree 4 case, it does not have a negative 1 out front. How do we generalize? Well, in the cases where n is odd, it should be negative. In the cases where n is even, it should not be negative. So that's where we get negative 1 to the n. So any questions with this? Any questions? Okay, so again, as I mentioned before, the rest of today, all we're going to do is look at some cool problems. In one of them, we'll actually introduce a new type of polynomial, but it's really just for the purposes of the problem. Okay, so this one's probably a little challenging. We'll get to it a little later. That's also pretty hard. Also pretty hard. Also, okay, they're all going to be hard, but let's start with this one. Okay, this one was actually on the final from last semester, but I don't think, I could probably count on my hand the number of people who got part A. I don't know if anyone got part B. So, I'll give you a couple minutes, try and work on it. Okay, half of the battle is figuring out what it actually means. And once you get that, and you get the trick, it's not too bad. Okay, so I want you to discuss, get out your pen and paper, work with the people near you. It should be a group activity, and then we'll come back together. Okay, we'll take up part A for now, and then I want you to keep discussing part B. So does anyone have any ideas for part A? Yeah. How to get there?
You would well, based on that polynomial, you know the roots of the polynomial are 1, 2, 3, up to k.
Right.
And so then, therefore, you know the sum of the roots. And from the Vieta's formulas, you know the sum of the roots is the coefficient on x to the k minus 1 over the coefficient of x to the k.
Yeah.
And we can tell by looking at this polynomial that the coefficient of x to the k is going to be 1.
Yeah.
So the sum is just the coefficient we're looking for.
Exactly. Well, the negative of the coefficient we're looking for. Yeah, exactly. So here, so the first thing to note is that the coefficient, like, sure, you can expand this out to look something like x to the, a sub k, x to the k, plus a k minus 1, x to the k minus 1, plus blah, 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 plus a2x squared, plus a1x plus a naught. Here we know ak is going to be equal to 1 because there's no leading coefficient, right? You multiply all the x's in the beginning, you'll get 1. So, it doesn't really make it easier, but it's something that we have to keep track of. Okay? And what we're looking for is this. And remember, the sum of the roots is always, so the sum of the roots is always negative a sub k minus 1 over a sub k. Right? We just looked at that. And here, a sub k is just 1, so the sum of the roots is negative a sub k minus 1. But that just means a sub k minus 1 is the negative of the sum of the roots. Is that clear? Any questions so far? Now, how do we find the sum of the roots? So now this goes back to when we talked about induction-ish, when we figured out how to find the sum of the first k natural numbers. Does anyone remember what that expression was? Sure.
Was it
n times n plus 1 over 2. Yeah. Good. And so, I guess we can come over here, say recall. The sum 1 plus 2 plus blah, blah, blah plus n is equal to n times n plus 1 over 2. Remember, in general, the sum of an arithmetic series is the first plus the last divided by 2 times the number of numbers. What's the first term here? 1. What's the last term here? N. Divided by 2 times the number of numbers we're summing, which is n. N times n plus 1 over 2. Okay, but that, again, that's something that you should remember. And so, what's the sum of the roots in this case? So negative this sum, which is negative k plus 1 over 2. Okay, so this ties in many concepts from the semester, which is why I like this question so much. Okay, so I'll let you keep working on trying to find the coefficient on x. This one's significantly trickier. Okay. So let's come back together for this one. Okay, so let's just put this on the next slide. And so remember, our polynomial is something like x minus 1, x minus 2, blah, 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 x minus k minus 1, x minus k. And we want the coefficient on x. Any ideas? Any ideas? Okay. Let's look at an example with degree 3 and degree 4 first. Okay? Going back here, we notice the coefficient on x is what you get when you multiply 3 terms together, or 3 of the roots together, and you sum all the possible ways you can do that. Okay? And as I mentioned before, it's the same as picking one root not to multiply and then multiplying the rest. Is that clear? What I can actually do, though, is rewrite this sum. So I can rewrite R1, R2, R3 as R1, R2, R3, R4 divided by R4. You agree with that? I can rewrite R1, R2, R4 as the product of the same thing divided by R3. I'm multiplying them all, but dividing out one of them. Is that clear? I could do the same for R1, R3, R4. That's what I get when I multiply all 4 and divide out R2. And I could do the same with the last one as well. Anyone see where I'm going with this? Yeah.
So like for our case, since the roots are just the natural numbers up to k,
yeah,
like each product in the numerator would just be k factorial.
Yeah.
And then you just divide it by 1 plus divide by 2, et cetera, et cetera.
Exactly. So let's extend this to, just to make it a little more clear, let's look at this case as well. The degree 3 case. And suppose we're using the polynomial we have. Okay, so let's just say R1 is 1, R2 is 2, and R3 is 3. Okay, that's just the case we're looking at. Well, again, we could rewrite R1, R2 as R1, R2, R3 divided by R3, and so on and so forth. So I could really rewrite this sum as R1, R2, R3 times 1 over R1 plus 1 over R2 plus 1 over R3. Is that clear? So I can write the coefficient on the linear term, so on the x term, as something like this. Okay, because it's just taking, in the degree n case, it's taking n minus 1 of them at a time and multiplying them. Well, that's the same as taking all n, multiplying them, and dividing out each one individually. Is this idea okay? And so, in our case, the product of all the roots is just k factorial, right? Because our roots are just 1 through k. And then I divide by 1 over, or then I multiply that by the sum 1 over 1 plus 1 over 2 plus dot, 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 all the way until 1 over k. So let's do that. Let's go over here. And so, for us, the coefficient on x to the k will look something like R1, R2, R3, dot, 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 times R sub k minus 1, plus R1, R2, dot, 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 R k minus 2, RK. So the reason I'm writing it like that is because it makes it clear which one I'm skipping, plus R1, R2, dot, 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 RK minus 3, RK minus 1, RK, plus, and I'm not going to write all of them because there's who knows how many. I can write it as R1, R3, RK, plus R2, R3. Okay. So that's really what we're looking for. And we know the sign on it will be positive because the sign on the next term will be negative because I told you K was on. But really that's not important. It's about this sum. And what I claimed to you was this is the same as writing the product of all the roots And then first dividing out root k, then dividing out root k minus 1, and then, subsequently dividing out each of the roots. And then again, in our case, this is equal to k factorial because the roots themselves are just 1, 2, 3, dot, dot, dot through k. Multiply them all, that's k factorial. And then I have 1 over k plus 1 over k minus 1 plus dot, dot, dot plus 1/2 plus 1. So to write this a little more succinctly, say k factorial, the sum I goes from 1 to k of 1 over I. And that is the final answer. So any questions with this? It really uses a lot of properties that we sort of talked about in the course, but I think that's why it's a good question to do towards the end. Any questions? Great. Let's work through this one. Suppose the polynomial x cubed minus alpha x squared plus beta has 3 roots, one of which is equal to beta squared. What is the sum of all possible values of beta, and what is the product of all non-zero possible values of beta? Okay, and look at the hint, because there's both a very easy way to do this and a very complicated way to do this. They both arrive at the same result. But I don't want to give away the trick. But discuss it again with the people near you. Keep working. Don't look at what I'm writing up here. Okay, let's come back together. Because it's so complicated, I've started the solution on my own. Okay, so let's see. Does anyone get the trick, by the way? Okay, don't say yeah, we'll walk through it. So let's suppose, because we've been talking about Vieta's formulas, we do that. Okay. So we're told one of the roots is equal to beta squared. Right? So we have R1, R2, and R3. Let's just say R3 is equal to beta squared. We don't know what R1 and R2 are. Well, let's look at the coefficients in our polynomial. The coefficient on x squared is negative alpha. That tells us the sum of the roots will be alpha. Right? So I can say R1 plus R2 plus beta squared is alpha. Everyone good so far? Cool. I can also say that the symmetric sum of multiplying two of them together and adding them is 0. R1, R2 plus R1, R3 plus R2, R3 is 0. And then lastly, I can say the product of the roots is negative beta. Okay? And what I can do is rearrange the first equation to be in terms of R1 plus R2. So I have R1 plus R2 is alpha minus beta squared. I really got that from rearranging this first equation. I can do some clever common factoring in the second equation, right? I can start off with, this expression over here. And what I can do is take out a common factor of R3, which I know to be beta squared from the last two terms, right? So I have R1 plus R2 is 0. But I already have an expression for R1 plus R2. That's this guy over here. And I can rewrite R1, R2 as R1, R2, R3 divided by R3. It's the same trick we used in the last problem. So I can write this as R1, R2, R3 over R3 plus R3 times R1 plus R2 is 0. Now I actually know each of these things. I know R1, R2, R3, it's negative beta. That's given from the polynomial. I know R3, that's beta squared. And I know R1 plus R2, that's alpha minus beta squared. Okay, so it's really just writing out the expressions in terms of Vieta's formulas, plugging in the variables we know, and now we can simplify this mess. And let's see what we get. Let's multiply through by beta squared. Okay, so then I have negative beta plus beta to the 4, alpha minus beta squared is 0. Again, doing a little bit of simplification, I could say negative beta plus alpha beta to the 4 minus beta to the 6 is 0. And just because I want the coefficient on the leading term to be positive, multiply through by negative 1, and I get beta to the 6 minus alpha beta to the 4 plus beta is 0. And now what's the coefficient on the second highest degree term in this expression? 0. Right? And so I can conclude that the sum of all possible beta right? Because all the possible values of beta are the ones that just satisfy this expression down here. I can conclude the sum of all possible beta is 0. Because the coefficient on beta to the 5 is 0. Does that sort of make sense? We started off with the relationships in terms of Vieta's formulas and manipulated them until I got an expression in terms of beta. And all of the values of beta that satisfy the original expression are just the ones that satisfy this, are the roots to this, right? Because it's something equal to 0. And the sum of all possible ones would just be the coefficient on beta to the 5. Well, the negative of the coefficient on beta to the 5. But that's 0. Okay. So does anyone see the trick now? Like, why do we not have to do any of this? Do you have an answer?
Just plugging b squared.
Yeah, exactly. So we could have arrived at the exact same result by just plugging in beta squared here. And it'll give you the exact same thing. You get beta to the 6 minus alpha beta to the 4 plus beta is 0. And you're done. So the point of this exercise, I guess, was to not just use the most fanciest thing you've learned. Right? You start off with the definition of what a root is. A root is just something that when you plug it into the polynomial, you get 0. And we have the exact same expression that we derived down here. And we're done. Is that okay? And it's not just a coincidence that we got at the same result. Something would be weird if we got a different result. Because beta squared is by definition one of the things that satisfies this expression. So if we got a different expression down here, something would be wrong. So it makes sense that we get the same thing. And yeah, the reason I wrote all that stuff up here was just to mislead you. Okay, so what's the sum of all possible values of beta? 0, right? Because there's no coefficient on beta to the 5. What's the product of all non-zero possible values of beta? Any idea? I think it's just beta. Because it's the constant term divided by the coefficient on beta to the 6, which in this case is 1. So it's just the constant term. The reason we had to say non-zero possible values is because if you let beta be 0, it satisfies the original expression. Doesn't work down here because we would have had to divide by 0 at some point. So that's why things would be weird. You have to consider that separately. Okay, so again, don't just jump to the fanciest, newest thing you learned. Think about what each sentence means. Does everyone get the point of this exercise? Okay, but it does work using these new tools, which is cool. Okay? I thought we were going to end early, but I don't think we are. Okay. Let's look at another example. Okay, and this one is pretty challenging as well. Let f of x be x squared plus 6x plus 9 to the 50 minus 4x plus 3. And suppose this function has 100 roots, r1 through r100. Determine, essentially, this sum. Okay, so I'll give you a couple minutes, work through that one. so this one uses a lot of everything again. Sums, binomial theorem, Vieta's formulas. Put it all together. Okay, a quick side note. I'll give you a couple minutes to keep working, but these three cubic polynomials, do you agree that the sum of the roots in all three cases is the same? The roots themselves are definitely not the same, but the sum of the roots is fixed. Okay, so that might give you some intuition for this problem. Okay, I'll walk through this one because the other two examples I think are cooler. Okay, so, well, let's start with our function set equal to 0 because we're looking at roots, and roots are just things when you plug them into the polynomial, you get 0. X squared plus 6x plus 9 to the 50 minus 4x plus 3. Set that equal to 0. So first, you notice that these exponents are to 100, and there's one simplifying step you have to make, and that's rewriting x squared plus 6x plus 9 as x plus 3 squared. Is that okay? So I can rewrite this really as x plus 3 to the 100, because x plus 3 squared to the 50 gives you x plus 3 to the 100. And I can add 4x and subtract 3 from both sides, and I'm left with that. And so now, I know that anything that's a root of f of x is just a thing that satisfies this expression. Because I just set the function equal to 0 and did a little bit of manipulation. And so what I can really do is say that for any root Ri, we can say that this holds true. Because the things that satisfy this expression, by definition, are just the roots of f of x. So then what I can do, similar to when we derived expressions for the sum, 1 plus 2 plus blah, 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 till n, 1 squared plus 2 squared plus blah, 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 until plus n squared, and so on and so forth. What did I do? I summed both sides, going from I is equal 1 to 100. So sum both sides. The sum I goes from 1 to n of Ri plus 3 to the 100 is the sum I goes from 1 to n of 4Ri minus 3. And now you agree with me that the thing on the left is just what I'm looking for. Right? I want R1 plus 3 to the 100 plus R2 plus 3 to the 100, so on and so forth. And that's really just what this is. So all I have to do now is evaluate the right-hand side. Is that okay? Great. So now, let's proceed. So I can break apart this sum into I goes from 1. I can really write this as n being 100. Of 4Ri minus the sum, I going from 1 to 100, of 3. Well, what's the sum of 3 100 times? 300, right? So I can replace this with a 300, and I can pull the constant of 4 out in front in this sum. So I really have 4 times the sum, I going from 1 to 100 of Ri minus 300. So now I just need to find this thing over here, the sum of I going from 1 to 100 of Ri. But what is that? It's literally just the sum of the roots. Do you agree with that? And we're talking about the roots of this original expression. But the roots of that expression happen to be the same as the roots of this expression, because the only thing that impacts the coefficient on x to the 99 are other terms of degree x to the 99, or of degree 99, right? Like adding this minus 4x plus 3 will not change the sum of the roots. Is that clear? So all I need to do now is find the sum of the roots of x plus 3 to the 100. So sum of roots of f of x is the same as the sum of the roots of x plus 3 to the 100. And that sort of tells you why I wrote this example over here. The only thing that impacts the sum of the roots are the first two terms. Everything else after that, you can change them. The roots themselves change, sure, but the sum of them does not change. That's why we only have to look at the x plus 3 to the 100, because the minus 4x plus 3 is not going to change the sum of the roots. Is that okay? Great. And so now, we go back to the binomial theorem. What is the coefficient on x to the 99? Right? Do you agree that the coefficient on x to the 99, the negative of that is the sum of the roots? Right? And so, we can say x plus 3 to the 100, it's probably x to the 100, plus 100 choose 1, x to the 99 times 3. Agreed? And plus blah, blah, blah. And so, what's the coefficient on x to the 99? 300. 100 times 3. So what's the sum of the roots? Negative 300. Okay? So I guess to write it a little more explicit, is equal to negative coefficient on x to the 99, which is negative of 100 choose 1 times 3, which is negative 300. So that means the sum thing over here is equal to negative 300. So I have 4 negative 300 minus 300, which is 5 times negative 300, which is really 1,500. So whatever value they were asking us to look for is negative 1,500. Is this okay? And again, we're going through this pretty quick. So I really recommend you, when you get some time, even if it happens to be over the summer, you really should just look through these slides again and see if you can work through these problems on your own. Okay? So the last two are pretty interesting. Okay. So now again, consider the example P of x is a2x squared plus a1x plus a naught with roots r1 and r2. Prove, using Vieta's formulas, that if R1 is complex, then R2 is the complex conjugate of R1. Okay? There's several ways to prove this. It's pretty easy to do with quadratic formula, but this is just showing you that you can use Vieta's formulas to do a lot of different things. And so what does complex conjugate mean? Well, first we have to answer, what does it mean for a number to be complex? And so a number is complex if you can write it as a plus bi, where a and b are real numbers. Okay? That means all real numbers are also complex, right? Because you can just set b to 0 and it still follows this. Okay? So if you want to throw it back to set builder notation, I don't know why you'd want to do that, but okay. You could say the set of complex numbers is a set of all numbers a plus bi, such that a and b are real numbers. Okay? And so what's the complex conjugate of a number? So if z is a plus bi, the complex conjugate of z is a minus bi. Okay, that's really all we have to know for this question. Okay, so prove using Vieta's formulas that if R1 is complex, then R2 is the complex conjugate of R1. So I'll give you a couple minutes to work through this, but what I'll tell you is assume R1 is a plus bi, and also assume R2 is c plus di. Show using Vieta's formulas that a has to be equal to c and b has to be equal to negative d. So what I mean by that is, so assume R1 is a plus bi and R2 is c plus di, and show a and c have to be equal and b has to be the negative of d. And if you do that, you show that R2 is the complex conjugate of R1. Okay, I'll give you a couple minutes to try and figure this one out. What I should have mentioned, whenever we're talking about polynomials, usually you assume all the coefficients are real numbers. So assume the coefficients are real. Okay, and it's very possible to have a polynomial where all the coefficients are real, but the roots aren't. So for example, x squared plus 1 is 0. All coefficients are very real, but roots are complex only. Okay, I'll go through this one just because I really want to spend time on the last example because I think it's very cool. Okay, so the whole part of this proof really revolves around the fact that all the coefficients themselves are real numbers, which means if you were to write them as a complex number, the b part would have to be 0. Is that clear? So what do we know? Well, we know that R1 plus R2 is going to be negative A1 over A2. And we know the product, R1 times R2, is going to be positive, actually, A0 over A2. Which are both real, right? So that's real. That's also real. Is that clear? So let's look at what we get when we add R1 and R2 and what we get when we multiply R1 and R2. Why don't we move this down here? We add R1 and R2, and again, we're assuming that R1 and R2 are arbitrary complex numbers, not necessarily conjugates, and we're going to show that they have to be conjugates. When we add them, we get A plus BI plus C plus DI. But you can really write that as A plus C plus B plus D times I. But we know that this is equal to negative A1 over A2. Correct? And we know negative A1 over A2 is some real number. That means this B plus D part has to be equal to 0. Is that clear? And so what we can infer from this is that B plus D is 0, which tells us B and D are negative, negatives of one another. So that's part of the battle. And so we've really done this first part. So we know that if R1 is A plus BI, R2 is C minus BI. Now we just need to show A and C are the same, and then we're done. And we can do that with this product thing. So why don't we multiply A plus BI, C plus DI. That gives me A times C plus ADI plus BCI plus BDI squared. You okay so far? Okay, why don't we zoom in a little? And now we know I squared. Probably should have mentioned this before, but I squared is negative 1. So I can write this as AC minus BD plus AD plus BC times I. Is that clear? Now, again, this is some element of the real numbers because it's just A0 over A2. And so that means AD plus BC has to be what? 0 also. And so we come over here. AD plus BC has to be 0. But I know B and D are opposites. So I can really write this as A times minus B plus B times C is 0. Which I can then write A minus C times B is 0. And we know B is 0 because otherwise, we know B is not 0 because otherwise the two roots would, I guess they'd still be complex, but they would be purely real as well. So we wouldn't do this whole exercise. We're assuming that R1 is complex only because if B was 0, R1 would just be A, which is just a real number. So we can safely divide by 0, giving us A is equal to C. And so what we did was we used the properties outlined by Vieta's formulas to show that if R1 is some complex number A plus BI, and R2 is some complex number C plus DI, and they're both roots to A2x squared plus A1x plus A0, it has to be the case that A is equal to C and B is equal to negative D, which implies that if R1 is A plus BI, then, a different color, R2 is A minus BI, which proves that they're complex conjugates of one another. Because the conjugate of A plus BI is A minus BI. And so we're done. Is this clear? Right, and there's probably other ways to prove this that are more straightforward. But again, the point of this is to illustrate the fact that you can do this with Vieta's formulas. Sounds good? Okay. So now the last one I think is the coolest. So suppose P of x is a polynomial of degree n. And we're going to define this new polynomial, now P star of x, which is equal to x to the n times p of 1 over x. And we'll call this the reciprocal polynomial. So any polynomial p of x will have a reciprocal polynomial p star of x. Is that okay? And so, one thing you might note is that if R1 is a root of P, 1 over R1 will be a root of P star. Do you agree with that? And vice versa. So the reciprocals of the polynomials, the reciprocals of the roots correspond. So what we can look at is suppose R1, let's just say R, is a root of P of x. Then let's look at P star of 1 over R. Well, that would be, 1 over R to the n of P of 1 over R, which would give you 1 over R to the n P of R, which is what? 0. Because we're assuming, we're assuming R is a root of P of x. So we know that if R is a root of P of x, 1 over R is a root of P star of x. And we're assuming, not again because I didn't say it before, but assume R is non-zero, because then you couldn't do this. So we're saying if R is a root of P, 1 over R will be a root of P star, just by the way it's defined. We can also work in the other way. Now suppose 1 over R is a root of P star of x. Is a root of P of x. Let's see here. No, this should be P star of x. And again, we're going to assume R is non-zero. So first we prove the forward direction. If R is a root of P, then 1 over R is a root of P star. Now we're going to do the opposite thing. So now we're going to assume that P star 1 over R is 0 by default. Well, what does this mean? Well, it means we're looking at 1 over R to the n times P of R is 0. But we assumed R was non-zero, so this term cannot be 0. Okay? And so since 1 over R to the n is never equal to 0, we must have P of R is equal to 0, i.e. R is a root of P of x. So what does this all of this mean? So I guess this is one direction, this the other. It says R is a root of P if and only if 1 over R is a root of P star of x. Is that okay? So we did the two directions. If R is a root of P, we showed that 1 over R is a root of P star. And if 1 over R is a root of P star, we showed that it must mean that R is a root of P. So that means if P of x is one polynomial, you can take its, make all of its roots its reciprocals, the polynomial you'll get out is P star of x. Is that okay? So if the roots of P are 1, 2, and 3, the roots of P star will be 1, a half, and a third. Is that okay? So that's one thing. But now also, let's just look at the relationship between the coefficients of P and the coefficients of P star. And this is what I think is really fascinating. So why don't we look at P of x being ax squared plus bx plus c. Nice, okay? Now, let's look at P star of x. And by definition, I think we said that was x squared P 1 over x. Right? So we'll say this is x squared a times 1 over x squared plus b times 1 over x plus c. Okay? And so this is x squared times a over x squared plus x squared times b over x plus cx squared. You see where we're going with this? Kind of. The x squares cancel here. This cancels. And we're actually left with cx squared plus bx plus a, which is what you get when you reverse the order of the coefficients. Does that make sense? So it happens to be the case that the reciprocal polynomial of a given polynomial, same degree, you just reverse the coefficients. Okay, let's work through an example. So suppose we have f of x is x squared minus 7x plus 6. Okay, what are its roots? 1 and 6, right? Is that okay? Let's see what happens when we expand out x minus 1, x minus 1/6. Let's set it equal to 0. Okay? X squared minus 1/6 x minus x plus 1 over 6 is 0. And so, a little nuance I should have noted here. So let's continue. What do you get when you subtract 1, or when you add 1 and a sixth? I think you get 7/6, right? And now we multiply through by 6, and we get 6x squared minus 7x plus 1 is 0. Which is what you get when you reverse the order of the coefficients here. So the roots of this first polynomial, x squared minus 7x plus 6, are 1 and 6. The roots of when you reverse the same thing are 1 and 1 over 6. So you take the reciprocals of the roots. Okay. One little nuance here. I think you can only generalize this to be the case when the polynomial is equal to 0, like when we're looking at the roots. Because if you look at when I looked at x minus 1 and x minus 1/6, I had to multiply this, what I've circled here, by 6 in order for it to be the same thing. So we're looking at the roots, not the polynomial itself. Okay, so the main takeaways, if, let's just say a is a root of p, 1 over a will be a root of p star and vice versa, and the coefficients of p star are the reverse of the coefficients of p. Okay, so if we have a polynomial with roots 1, 2, and 3, and a polynomial with roots 1, a half, and a third, their coefficients will be the reverse of one another. Is that okay? Cool. And so we can try and work through a problem with this. Okay, but I'll walk through most of it together. So for example, A is another problem, really. Determine a polynomial with roots a plus 3, b plus 3, and c plus 3. Given that x cubed minus 3x squared plus 1 has roots a, b, and c. Any idea? And so what's the difference between a, b, and c, and a plus 3, b plus 3, and c plus 3? What's the difference? Think about this visually. What is the difference between a polynomial with roots a, b, c, and a plus 3, b plus 3, and c plus 3, visually? Any ideas? Sure. Yeah, it's shifted to the right by 3. Okay? And how do you shift algebraically a function to the right by 3? Well, you plug in x minus 3. So now we look at x minus 3 cubed minus 3x squared plus 1 is 0. Okay, well, we're really looking at the polynomial on its own. So now we just simplify all of this. Okay? You just have to remember this. X cubed minus 9x squared plus 27x minus 27. Oops, that should be Okay, minus 3x squared minus 6x plus 9 plus 1. And I think, whatever, let's just jump to Wolfram alpha, our good friend. It's x cubed minus 12x squared plus 45x. And x cubed minus 12x squared plus 45x minus 53. Sure, that was not really the point. The point of it was just seeing this trick. You plug in x minus 3. So now the question is, this is a polynomial with roots a plus 3, b plus 3, and c plus 3. What's a polynomial with roots 1 over a plus 3, 1 over b plus 3, and 1 over c plus 3? Well, it's the polynomial you get when you reverse the order of these coefficients. So if we can say the coefficient vector for this polynomial is 1, negative 12, 45, and negative 53, the reverse of that is just negative 53, 45, negative 12, and 1, which gives us negative 53x cubed plus 45x squared minus 12x plus 1. And jumping to Wolfram alpha, this was the first polynomial, right? With roots being these weird decimals. And this is the second polynomial. Okay, I'll just flip the coefficients. And to prove to you that one are the reciprocal of the other, why don't we look at them? So this one we have 1 over 2.46971. Here we have 1 over 1 over 3.65270, and the last one 1 over 5.87939. And you see that they're exactly the ones we have here. One's here, the other's here, the last one's here. Okay? So I'm not making it up. I don't think you thought I was, but. Okay. And so that's basically it for today. I'll put up the attendance link. We'll wrap up next class with some other applications of polynomials, a little similar to what we did at the end here. And then next week we'll start reviewing all the things we did in this course, and we'll go from there. And again, feel free to reach out if you think something's wrong with your grade or your attendance grade, or if you just want to talk in general.